All right, what's up, guys? We ready for some linear algebra? I'm just gonna be going over the five, I think, main topics that we learned over the quarter, and then we'll just go from there. I'm gonna try and make it like easy to understand, but we'll see. I mean, that's a sign of a good teacher, and I hope everyone walks away from this video knowing how to do all of these things with linear algebra and know what linear algebra is, because that's a really abstract kind of thing. But anyway, linear systems of equations. What is that? An equation is literally just like x plus y equals 5. Everyone's done that, right? And this is a linear equation because it's a line, right? You're not doing like y squared or x cubed or none of that, right? It's just a line. So if you were to graph this line, x plus y equals 5, or we could say y equals 5 minus x. So if you have 5 right here, it's just like, 5, and it's like, that's our line, right? A system of linear equations is just two or more linear equations. So let's say we have x plus y equals 5, and also x minus y equals 3. Or we could say y equals 3, x minus 3. Okay, now we're gonna graph that with a different pen. We got different colored pens up in here. X minus 3, so it would be something like, it goes down to like minus 3, it goes like up like that. And then we have an intersection, okay? All this first part of linear algebra is you have linear equations, you have systems of them, so multiple, and you're finding the intersection. That's all it is. Now, we do this with higher dimensions, typically 3 dimensions. So that would look something like, let me get my eraser here. It's gonna be harder to draw. If you know 3 Blue 1 Brown, just watch all of his videos and that would be the best. But it would look something like x plus y plus z equals 1. Instead of a line, it's a plane, which is still linear. And then you would have like 2x minus 3y plus z equals 5. And that's a system of linear equations, but in 3D. And I have an example here of like why this is helpful, right? So let's do this. This is gonna be a 2D example. Okay, when I am in my dorm and doing school homework, for every hour of work I spend time on, I'm really doing 30 minutes of homework, and let's be honest, 30 minutes of scrolling on Instagram Reels. But when I'm at the library, I spend 50 minutes on homework and still 10 minutes on Reels, because we got to get our Reels in. How could we represent this as a system of linear equations? Okay, well, let's say x, okay, I'm going to write this out first, and then we'll explain it. 30x plus 50y equals just some random a, and then we have 30x plus 10y equals another b. What do we think x and y are? Well, let me read it again. In my dorm, I spend 30 minutes on Reels and 30 minutes on homework. There's 30s right here and here. Okay, so x, what is x? X could be the hours that I spend in my dorm, and then y could be the hours I spend in the library. So then what would A and B mean? This is my total time studying. And this is my time on Reels. So using this system of equations, we can find stuff out, like how many, what did I say here? If I studied for 3 hours in my room and 4 hours in the library, what does that mean, right? So we know that this is time spent in my dorm, X's, and Y is time spent in the library, right? So if we just plug in 3 hours for X and then 4 hours for Y, we get 30 times 3 plus 50 times 4 equals the amount of time I spent studying, right? So that would be, I believe, 290 minutes studying. And then same thing for this, it's 30 times 3 plus 10 times 4 equals 130 minutes on reels. And so then you can use this to go backwards and you can say, okay, I want to spend 300 minutes studying. What combination of being in my dorm and being in the library would I need to do? That's not a good example because you could just spend 6 hours in the dorm. But let's say it was like, I want to spend 60 minutes studying. Well, I could do 1 hour in the library and 1 hour in my dorm, and that would add up to 60 minutes. But then I'd also have 40 minutes of real time, which is necessary. And that's just a 2D example, but I don't want to write more, so I'm not going to do a 3D example, but that's what we mainly work with. Next step, that's like the first main thing. Next step is something called Euclidean space, which I don't even know what that means. Actually, I do. All it means is Rn. What is Rn? It's just the dimension we're working with. So with linear algebra, you can get up to infinitely many dimensions, right? Which doesn't make sense. So we live in 3 dimensions, so that would be R3. R3 is 3 dimensions. That's our world. R2 is just like this whiteboard. It's flat, right? R1, just 1 point. There's 1 point right there. Euclidean space. What is in this chapter? Vectors. I hope I'm not disrupting anybody studying for finals. Vectors. What is a vector? That's right. A vector has direction and a magnitude. So it's basically just an arrow. It's literally an arrow. Vectors are used for different applications in different fields. So like in physics, you could have like a box, right? And then the vectors are at like different spots. You could have like the force of gravity, and then you have like the force of friction or something is like right here if it's like moving. They're at different spots, right? But in math, we use vectors, they all come from the origin. So it would literally just be like, let me use different colors because we're fancy up in here. They all come from right here. So no matter what they are, how long they are, they just come from the origin. A way to write vectors, there's a lot of different ways to write vectors too, is like you write like a variable symbol, just any letter with a little arrow on top with a little hat. It's pretty cute. Equals, we can do it like this. A column vector is just straight up and down, 1, 2. And what is this? Use like square brackets. And what does this represent? This, in 2D, this is the X, this is the Y coordinate, and then you can be like, this is the Z coordinate if you use 3 of the tip. And then the base goes at the origin. And that's all it is. All right, now let's think about this word I'm about to throw at you, right? The next word that took me a while to understand actually, but it's not that complicated, is span. All span is the area that a vector can reach using like copies of itself, is like a way to put it. So, or multiple vectors, that's where it gets hard, right? So I'm just going to draw something out here. Actually, I'm going to draw this bigger because I don't really know what you guys can see. We're going to draw this. That's a little bit bigger. Just in 2D, right, is what we're going to stick with. X and Y. We all know that, right? We're familiar. And let's stick with our V. We'll write these in blue. V equals our 1, 2 vector. So let's say we have, our grid marks 1, 2. So it's like this. That is V right there. And then we're going to use a different color because I have so many colors. We're going to say W equals, well, no, let's do it this first. V is that. So if I said, what's the span of V? What do you think that means? All that is literally this line right here along V. Why is that? If you use multiples of V, either positive or negative, so it's just multiplying V by a constant, where does that take you? If you stack it on top of each other, you just go up the same amount. That's another arrow. That's another arrow. Or if you flip it, you go this way. You go this way. Boom. That's the span of one vector. When we add another one, that complicates things a little bit more, which makes sense, right? Because we're adding another element here. Let's go back to our W. I'll redraw V. W equals, we're going to change V, actually. I changed all mine. We're going to use something called unit vectors, which unit in math just means 1, like a length of 1. So 0, 1, and then, or 1, 0, and then 0, 1. Boom. I have so many markers in my hand. That's too much. Okay. V, we're going to draw these grid marks, is just going to be, x coordinate is 1, y coordinate is 0, so it's just going to be this line right here. That arrow. Yeah, you can see that, kind of. And then W is just that line right there. Okay? Now, I'm going to tell you something. These two vectors, the span of these two vectors, which is written as the span of, 1, 0, and 0, 1, is all of R2, is every single thing. And why is that? Using combinations, using scalar multiples of these two vectors, we can get anywhere in 2 dimensions, anywhere in R2. And think about why that is the case. I mean, it's kind of simple. We can flip it, and we can flip either one, multiply them by any amount. We can get everywhere. And that is called linear independence. Linear independence. That just means these vectors are not similar to each other, is what I say. So the best way to describe this is an example. You see over here? Actually, I'll go down here. An example of two vectors that would be similar to each other, or dependent is the other word, is 1, 2, and 2, 4. Why are they dependent on each other, or why are they similar? Well, look at that. 2, 4 is a scalar multiple of 1, 2. That's not good. That's not good. Another way to say that is that this vector 2, 4 is already in the span of 1, 2. 1, 2 can reach 2, 4 by itself. That doesn't need 2, 4. It's useless, Yeah. So that's really all it is. And then you can go into 3 dimensions, right? So then you have your 1, 0, 0, 0, 1, 0 is your y, and then 0, 0, 1 is your z, and then that can get you everywhere. And there's ways we can go about finding if vectors are linearly independent or not. Because then what if I said, okay, we have these two vectors, but then we also have 5, 3. Whoa, That's 3 vectors. They're kind of tilting, sorry about that. That's 3 vectors in 2 dimensions. What does that even mean? Well, we already know that these 2 vectors are in the same span. They don't do anything, you know, they only need one of them, and one of them. So we can just cross it out, right? If we said the span of this set, you know, and then we can say, okay, well, are these 2 similar to each other? Well, if we want to get 5 in this one, we multiply it by 5. So 5 times 1, 2 is just 5 times each entry. It's just 5, 10. Well, that's not the same. So this would increase the span of the set. And a rule of thumb is if you have 2 independent vectors in R2, they span everything. And you might ask why. Well, V and W, that's all we need, right? We just need one to be 1, 0 and one to be 0, 1. It's harder to see with these 2, but we can actually do something called row reduction and reduce these vectors down to this exact form every time if they're independent. And there's something called the unifying theorem, which is like 13 things that, like, if it's independent, then it's also invertible, then blah, 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 blah. But that's above my pay grade. So we're moving on now. Oh, here we go. This is important. This is important. Is any of this important? No, I have finals to do. And I've been at the library for like 10 hours today, but it's part of the freaking life. This is what dreams are made of right here. Matrices. Plural. Or just singular matrix. A matrix is just a bigger vector. What does that mean? An example of a matrix is like 1, 2, 3, 4. Okay? It's just, you know, it's wider. That's all it is. But why do we use them? What are they for? You know? Linear equations. You remember when I was talking about that? Linear equations. So let's bring back some of the ones we have. We had x plus y equals 5. And we had, I'll write it like this actually. X minus y equals 3, I think. We can write this as a matrix. All right? And you're not going to believe me, but bear with me. Boom. 1, 1, 1, minus 1. Line 5, 3. This is called an augmented matrix. And if you can see what I did here, all I did was take the coefficients of these variables, right, and put them in. Literally, it's the same form. You know, you can draw the 1, 1, 1 right there. And you literally just put them in. So if it was like 2x right here, and like let's say it was minus 3y, right? 2 minus 3. Okay? That's all it is. Super simple. Okay? Yeah, augmented matrix. Boom. Why do we use these? Because they make it easier to solve these problems. Okay? Because like I know in 2D it's like you can probably, you know, find the intersection of this, right? You just do some algebra, some basic algebra, move it around. But we're thinking small because the same rules are applicable in 3 dimensions, 4 dimensions, and many dimensions, right? So let's actually take this example. We are going to row reduce it, like what I said before, and we're going to use it to 1, find a solution, and 2, see if these, whoa, I got ahead of myself there. We can also write this as vectors, okay? We can write this in vector form. How we're going to do that is we're going to take out the x, and we're going to take out the y, okay? We're going to say x times, you know, I said a matrix is just a big vector. X times 2, 1, the coefficients, plus y times the coefficients of the y's, 1 minus 3, equals, just this, make that a vector, 5, 3, right? Boom. And so all this matrix is doing is taking this right here, which is just like, you can kind of see how we get there. Kinda, I guess. And then you can go from here by just saying that this is x, this is y. This column is x and this column is y, all right? We got that? Now we're gonna row reduce, all right? And all the row reduction rules are, there's 3, right? Let's say this is row 1 and this is row 2, okay? To any row, you can add another row to it or add multiples of the row to it. You can switch rows and you can multiply a row by a constant number. So using those rules, all of these are going to be similar matrices. They're going to have different determinants. That doesn't matter right now. What's a determinant? We'll get to that. Hopefully this doesn't go too long. I don't know how this is. I don't know. We're going to row reduce it. So what I'm going to say right now, our goal is to get this into the form 1, 0, 0, 1, and then A and B, whatever these are. Okay? I'm going to try and do that. That's my goal. It's like a game. It's like a puzzle, all right? Try and do it in the least amount of moves that you can. And it ends up being like kind of fun. It's kind of tedious if it's like a bigger matrix. We've done like a 4x4. Get out of here with that. But let's try and do this over here. So I'll write this matrix again: 2, 1, 1 minus 3, 5, 3. Also, this line is basically just equals. That's basically all it means. We're gonna say, okay, well I have a 1 right here, and I want to get a 1 right there. So my mind jumps to, okay, let's just switch them immediately. Just no thinking about it. So we're gonna say row 1 switch with row 2. Hopefully I'm not being annoying. So all it does is literally just everything on that row, switch it up, okay? That's all it is, right? And now we have this, okay? Well, now I know I want this to be a 0. I have a 1 right here, so this is, using my knowledge of row reduction, I can get this down to a 0. All I gotta do is say R2 minus 2 times R1, okay? Because we can add and subtract rows and multiples of them. That's all we gotta do, right? So now, what is my result? The top row just doesn't change. So we're gonna do 2 minus 2 times 1. So that'd be 0. That's what we wanted. And then we have 1 minus 2 times minus 3. Oh boy. The minuses cancel out. So it'll end up being 1 plus 6, which is actually 7. And then we have 5 minus 2 times 3. So that would be 5 minus 6 is minus 1. Hopefully I'm doing that right. It's all on the fly. And now we're getting closer to this form, right? So I'm just gonna jump over here. And I see the 7 right here. I can just divide that by 7 to get 1, right? So I'm gonna say R2, just divide by 7. Okay, and then what am I left with? 1 minus 3, 0, 1 minus 1 seventh. Now that's kind of gross, but that's kind of what happens. We get some funky numbers doing row operations. Now what if I told, now look at how close we are. We're 1 step away from row reducing this. And now I forgot to mention something. This, you could be done here, right? You could solve it from here. I'll explain that later, but this is called row echelon form. All that means is that it's diagonally, like decreasing down, right? So you have a number here, and then there's a 0 under it. That's what matters. And then there's another number. That's row reduced form. We're gonna get, or that's row echelon form. Whoa. Row reduced echelon form is where the money is. That's this form right here. That's getting into this. If we can get there, that's money. So now we're gonna say row 1 plus 3 times row 2. And now it works out nicely because that's a 0, so that doesn't affect the 1, the nice 1 that we have, and that just cancels out the minus 3. So now we have 1, 0, 0, 1 in our matrix. And then we have to add, or would be 3 minus 3 times 1/7. I'm going to just do a little, 3 can also be interpreted as 21/7, so I can make the subtraction easier. Minus 3/7 would be 18/7. Minus 1/7. Boom. We got into a form. But you might be asking, Carson, why did we do all that? That's our answer. Whoa, what does that mean? Remember I said this column is x and this is y? The way we solve these is by back substitution. So I'm going to show you how to solve it from here, but first, I'll show it right here. What this is saying, let's write it back into a system of equations. This is saying 0 times x plus 1 times y equals minus 1/7. Which also is just saying y equals minus 1/7. That's crazy. This is just saying blah, 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 x equals 18/7. So that is our solution. That is the intersection between these two lines right here. That's what we did. And the fact that we were able to get it into this form tells us a couple things. It tells us that these vectors that I erased, these columns that we used to make our matrix, are independent. And so that's how we can determine independence of vectors, is one way to do it. Now, how can we solve it from here? Well, we can just write out the equation again. This is kind of checking myself here. X minus 3 times y equals 3, and then 7y equals minus 1. Okay, so we're going to start here because we just have one variable. So then we say y equals minus 1/7. Well, that's what we got right there. That's good. Then we plug that in up here. This is what you've probably done before. And then we get x minus 3 times minus 1/7 equals 3. And then we're going to say x equals 3 minus 3/7, which you remember, that's kind of what we did. X equals, let's say 21/7 minus 3, 18/7. That is what we got right here. Math is pretty cool. That is all I wanted to do for that, but then I realized, what does this mean? Like, a big part of math is, what does it mean geometrically? And that's a tough question to answer, right? I was trying to do the intersection of lines, right? The intersection of lines, or the intersection of planes if you go to 3D and blah, 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 blah. Let's say we want to do multiply a vector by a matrix. My voice is kind of, this is a water break time. How are you guys doing? Take a break, I know there's a lot. Oh, water just tastes so good. And so does Monster. Don't forget to cap your pens, guys. Do not forget to cap your pens. Okay, this is where it gets kind of more advanced, so I'll see if I even know how to do this, right? Linear transformations. Those are some words right there. What does that even mean? I'll just give you guys an example here. Actually, I'm gonna make this bigger. X, Y. And let's say we have, I'm just gonna do in the same color, our unit vectors. Okay, that's at 1. This is at 1. Our V and W, but really they're called I and J, believe it or not. We can write these vectors. I'm going to say this is I and this is J. I equal, it's called I hat also, and J hat because they have little hats instead of the dots. It's kind of cute. is 1, 0, right? And then j hat is 0, 1. Okay? Let's say I wanted to transform these vectors. We can do it one of two ways. The first way is one at a time. So let's say, I don't know, give me a matrix. Here in the front, give me a matrix. 1, 2, 3, 4. Oh, that's a good one. That is a really good one. So let's say A equals the matrix 1, 2, 3, 4. This is not an augmented matrix, this is just a regular old matrix. Let's say I want to apply this matrix to these vectors. Well, let's do that. So it would be saying like I, let me get this, times, or A times I, right? And then A times J, right? What does this equal? This is just 1, 2, 3, 4 times the vector here, 1, 0. And this equals, what does this equal? How do we do that? Oh no. Are we rolling? We're going. All right. We're at 30 minutes. Holy shit. No one's watching this. Okay. All right. This is for the algebra fans here. How do we multiply a matrix and a vector? A couple ways to do it. One way to think about vectors or matrices in general, this is like the first row, right? This is the row 1 and this is row 2. This is also, funnily enough, if we made these into a matrix, that would be the identity matrix. And you'll find out why. So this is just saying 1 times the first row of A, of this, and plus 0 times the second row. That's all it is. That's literally all it is. So 1 times that. Well, what does that mean, right? False. 1 times the first column. Because a way to do matrix vector multiplication is you do the row of the matrix times the column, dot product, if you know what dot product is. So it'd be 1 times 1 plus 2 times 0, and then 3 times 1 plus 4 times 0. So that just ends up being 1, 3. And then if you do the same thing with this, you just get the other column 2, 4. And so that is now our transformed matrices. 2 and then 4 up here. So we have 1, 3, and then 2, 4. That's what happens. That's all it is. Oh my God, I'm tired. Guys, what time is it right now? It's 11 o'clock. It is 11 o'clock and I'm doing this shit. For the people, the people want it. So many of you guys asked for this. Was I gonna make this video anyway? Yes. Are many of you watching right now? Probably not. And that kind of makes it easier for me to do this. Oh boy. 2 more topics left. Determinants and eigenvectors. I'm just going to go very broadly over these. I'm going to redraw what I just did, right? So determinants. Determinants, these are the fun chapters, okay? I'm going to redraw the matrix, the vectors that we had, right? So we had our 0, 1, right? 1, 0. And then we had our 2, 4, which I don't know if that's not what that looks like. 2, 4, and then we had 1, 3. Okay, I need to do this. 4, 3, 2. They're not supposed to be intersecting. I drew that with the wrong color, too. Fuck. I don't know how freaking, what is it, black pen, red pen? You guys know him, he's the GOAT. Okay, I'm gonna pick different vectors that are better. This will stay 2, 4, and then this will be like 4, 2, just so it looks better. Okay, so this is getting mapped to that, that is getting mapped to that. So it's like squishing it a little bit. What does this matter? Okay, how does this play into the determinant? Let me do a little something for you. I'm gonna pull out a different color. An ink capsule like broke in my bag, so like just gonna ink all over these markers, but we ride. Let's say I made a grid with my I and j vectors evenly spaced, okay? Using the vectors themselves. So I can make a box, right? I can go like, keep going like that, right? A grid. Can you see that? Well, that doesn't help. Can you? Not really. Hopefully. No, that doesn't help. We'll just roll with it. That's our grid for the 1, 1 vectors. But now we transform them. We have a new grid. We have a new grid, ladies and gentlemen. What does this grid look like? Well, the rules of these grids is that they're made up using the vectors and they're evenly spaced. Every patch on the grid, there's no like differences, and they're all linear because we're doing linear transformations. So if I just put this vector right here and this vector right there, well, that doesn't look very good. Sure enough, if you did that enough, surely it's kind of big, but you kind of see the idea. You get a bigger grid, and it's like a parallelogram now, kind of vibes, Why does this matter for the determinant? What the determinant is, so we said A was our matrix, right, that transformed these vectors into that. I'm going to draw in pink because that's a good color. Determinant of A is equal to what? If I said I want to find the determinant of A, this transformation that took these vectors into those vectors, right? The determinant of A is equal to the scalar multiple multiplier to the change in area. Scalar multiple to the change in area. So the area of this, we'll go back to our green here. I have this here too, which I should have been using the whole goddamn time. I have a little bit. Scalar multiple of area, what are they doing? This grid, the 1, 1 grid, right? Length 1, 1, and these were where our vectors were. So the area of this grid, of this box, is 1. Can I draw 1? Is 1. Well, what's the area of our parallelogram, you might ask? We had, this point was 4, 2. This point was 2, 4. Well, what's the area of that? What's the area of a parallelogram? A couple ways we could go about this is by using a triangle and doing stuff like that. I'm going to change these. Let's pretend it's not a parallelogram. This works for a parallelogram, but I'm too stupid and too tired right now to think of that. So we're going to say instead of a parallelogram, it's literally just a scalar. It's literally just a bigger square of like 4 length sides. So the area of that is 16. I can do 4 times 4 is 16. So what's the determinant there? 16. That's what it means geometrically. And now, I think the only people here are the ones that care about math. I'm going to go a little crazy with it to give you something to look forward to if you plan to take this class in the future, I suppose. What's the determinant of this 3 by 3 matrix? Is it 1, 2, 3, 4, 8, 12, minus 1, 3, 5. Now it's not so easy, right? This is not only it's in 3 dimensions, it is not easy to see. What we could do is row reduce this matrix here, but the determinant changes when you row reduce it. If you row reduce by switching rows, that changes the determinant. It does change the determinant. By negative, it flips it. If you subtract rows, any combination of rows or add them or whatever, it actually doesn't affect the determinant. But when you multiply a row by a scalar, it multiplies the determinant by that scalar. So we could row reduce this and then get the determinant that way. There's also another way called cofactor expansion, which basically is just writing out the determinant the long way. And if you've done cross product, you've done that before. So we could say the determinant of 1, 2, 2, 1 is equal to, you multiply along the diagonal, the first diagonal, and then you subtract the multiple of the other diagonal. So do 1 times 1 minus 2 times 2 is equal to minus 3. That would be the determinant of that matrix. Now that's like a little trick, right, for 2 by 2s. How can we use that to take the determinant of this? It's really difficult, but the way we go about it is literally just, color. We take the first term and we multiply it by the determinant of this matrix, of this submatrix. This is called the minor of A, so it's the 1, 1 minor, or you could write this as like M, 1, 1. It's what happens when you take the first row and the first column away from A. Is the idea behind that, but that doesn't really matter. That's how you use to do that for the n dimensional, determinants, but we're not really caring about that. And then, so we're gonna write that out, right? 1 times the determinant, because we know how to do the determinant of 2 by 2. That's easy. We've been doing that. That's just our neat little trick right here. 1 times the determinant of 8, 12, 3, 5. Then we're just going to keep going along. We're going to do this term, this 2. You can do any row or any column to choose to go along. But now we're going to do 2, but it oscillates. So it goes plus, minus, plus, minus. So now we're going to do minus 2 times the determinant of what matrix? Getting rid of this row and this column, it's 4 minus 1, 12, 5. Whoa. Okay? 4 minus 1, 12, 5. And then we have one more. I bet you could guess what we do with this last 3 here. 3 times this determinant of that matrix. I'm just going to put over here, and it's plus again, plus 3 times the determinant of this matrix, which is, oh, for this one you just squish them together. Well, the middle part doesn't matter. You just squish them together. We're going to 4, 8, minus 1, 3. And that's how you would do that. A good way to do it is if you have if you have like a matrix that's like 1, 0, 2, 2, 2, 2, 0, 0, 5, what row or column would we might want to cofactor expand upon to get the easiest determinant? Because it's all going to equal the same no matter which row or column you choose. Well, I would say we choose this bottom row because these two of these coefficients are 0. So then all we have is 5 times the 3, 3 minor of this, would just be 5 times the determinant of this, which is 2. So 5 times 2 is 10. We just found the determinant of a 3 by 3 matrix super easily. That's only if there's zeros. Also, of a diagonal matrix or a triangular matrix, which is just like zeros in all part in the lower diagonal or upper diagonal, or it's just along the diagonal is terms. The rest are 0. The determinant is just multiplying all the diagonals, all the terms on the diagonal. That's all it is for that, which you can sometimes use to cheat yourself a little bit. And real quickly, just gonna wrap up here because I'm tired and I don't know what I'm gonna eat, but that's okay. Got some chips. Eigenvalues and eigenvectors. This is what we learned most recently. It's eigen stuff, basically. They put eigen in front of everything and think they're cool. Like, I've heard eigenvectors, eigenvalues, eigenbasis, eigenspace. I'm an eigen, you know. What's an eigenvector? Let me take you back to the idea of transformations, right? Let's say we have this vector that looks like 3, 2, right? 3, 2. And we want to apply some linear transformation to it. What if when applying that linear transformation, the vector stayed the same? Or the vector, more specifically, it stayed on its span. So all the effect of that transformation was multiplying the vector by a scalar. Okay? And matrices, when a matrix is a transformation for all vectors, right? So there's only going to be a handful of eigenvectors. The eigenvector is the vector that when transformed linearly stays on its span, okay? And then the amount that it's scaled by, so let's say after some linear transformation, this vector is now -6, -4. The eigenvalue would be -2, because it's -2 times that equals -6, -4. There are ways to compute eigenvectors using eigenvalues in any matrix and set it equals 0. You can find the null space and the nullity and blah, 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 blah. There's so many vocab words, and I'm working on my note card for my final on Tuesday. It's pretty brutal. But that's it. That's all I'm going to do. If you want part 2, let me know. But probably won't be doing one. Have a good day. Good luck in finals for those of you in college.